We proceed in the analogy of the gradient vector, and we will see how it is really useful. Gradient vector is not mere a derivative. The way we think that gradient, the way we calculate the differentiation of any algebraic equation. So what is special in if we differentiate something and give shape of a vector? So that is a question, that how it is different from if I have a function fx or y equal to fx, it has a function dy by dx is derivative. If dy by dx is derivative, then it is nothing but a slope at any point x0 x. Simple, right? Means if I have if I have if I have this as x-axis, this as x-axis, and this is the line, this is the fx on x-axis, if this is the fx on x-axis, then any point derivative is tangent. But if I calculate derivative vector or gradient vector, then it is perpendicular. This is what we saw. If I take each point on the curve not an algebraic equation rather than as a kind of a position vector, then gradient vector is tangent. Both way we have seen. Why gradient vector is important? Why gradient vector is important? Anyway, importance we will see. So we have seen now the gradient vector of a circle, that is x square plus y square equal to a square, that is 2x plus 2xi plus 2yj. And we also saw that if I have x square plus y square equal to a square, then actually internally it is from a 3D. It is if directly if I am calculating actual derivative, actual gradient vector is if I have x and y, and then we are calculating the gradient vector, then x and y gradient vector is nothing but it is internally it is function. I mean, if I have x square plus y square equal to radius square, x square plus y square equal to radius square, and we simply go and calculate the gradient, that is 2xi plus 2yj, 2xi plus 2yj directly if I am calculating gradient, but gradient should happen based upon some independent and dependent component. If that is true, then x square plus y square equal to a square, x square plus y square equal to a square should be considered in two fashion. It is if I am calculating the gradient of x square plus y square equal to a square as 2xi plus 2yj, 2xi plus 2yj. If I calculating the gradient like this 2xi plus 2yj, this proves that both are independent components. Gradient vector generally we calculate dependence versus independence. That is the way. Like if I have a parabola, if I have a paraboloid, if I have a paraboloid, if I have a paraboloid, I mean take only half. Okay, don't consider the top one. Okay, so this paraboloid from here you can see it is going like this and up to here. Top, just discard it. So this is typical case of a paraboloid. If this is the case of a paraboloid, means down it is like this and it goes like this. This is the case of a paraboloid. If this is the paraboloid, then what is the equation of paraboloid? Then it is z equal to x square plus y square, or fxy equal to x square plus y square. Now, if that is the case, then if I cut this, if I cut this, okay, cut this. from from that is any xy plane at some z value, just cut it. If you cut it, then cross section, the thin cross section, you slice it. Slice in the sense, don't cut in two half. Take a slice. Then that slice is, take a slice, then slice is a circle. If that is a circle, if that slice is a circle, take a slice, slice is a circle. If that is a circle, then equation is z, now z it at a constant level. Consider that z is 2. What is the equation of that circle? What is equation of paraboloid? Z equal to x square plus y square. Now take z as any particular value and then make the formula again. Z equal to 4. Consider z equal to 4. Then it is 4 equal to x square plus y square. 4 equal to x square plus y square. So nice it is. What we are trying to see. If x square plus y square equal to 4, what is the set of x and y values where x and y both are independent? Where x and y both are independent. X is independent, y is independent. When both are independent, and can we keep changing the value of x and y? If we keep changing the value of x and y when both are independent, then it should result in 4 only. If x is 0, then y is 2. When x is 2, then y is 0. When x is 1, then y is the square root of 3, like this. So you will get set of so many xy points where if you do x square plus y square, then it becomes 2 square. So it is a nothing but cross section of a paraboloid. It can be a cross section of a sphere also, where equation of sphere is x square plus y square plus z square equal to a square. Now consider z equal to 2. Z equal to 2 and radius z equal to 2 and radius equal to 4. If that is the case, then x square plus y square equal to 16 minus 2, 4 means 12. Square root of 12 whole square. Same thing, right? Means if you take a sphere, if you take a sphere and cut this sphere again, if this sphere is centered at the origin, consider it is centered at the origin. If this is the equatorial plane, if you cut this at one location at some height, consider that some height is 2 and radius of the sphere is 4. Then it is x square plus y square plus 2 square equal to 4 square. Equation is x square plus y square equal to a square root of 12 whole square. Means this turns into that cross section circle turns into a circle of radius square root of 12. Okay, but anyway, now if someone says what is the gradient vector of x square plus y square equal to a square, anything, quickly we say 2xi plus 2yj. If it, but actually the situation is that circle, if we are calculating gradient like this, considering x and y as two independent components, considering x and y as two independent, if I say gradient of x square plus y square equal to a square, and immediately I say gradient of this equation is 2xi plus 2yj, I am considering x and y as independent component. If they are independent component, then what is dependent component? Actually, this is cross section of 3D diagram, either parabola, paraboloid, or sphere. Okay, but anyway, leave the concept now. So I'm trying to tell you that what is the scenario behind the scene, what is the scene behind the front scene. What is the back scene? So back scene is x square plus y square equal to a square and gradient is 2xi plus 2yj. Then actually it is a cross section of either a paraboloid or a sphere. In that way only, then if that is the case, so if it is a paraboloid, then z equal to x square plus y square. What is dz by dx? 2x. What is dz by dy? 2y. What is gradient vector? 2xi plus 2yj, right? If it is a sphere, then it is z equal to a square minus x square minus y square square root. What is dz by dx? Then it is minus x divided by square root of a square minus x square minus y square. Then the gradient vector is dz by dxi plus dz by dyj. If that is the case, then it is minus x divided by square root of a square minus x square minus y square I plus minus y divided by a square root of a square minus x square minus y square. If you calculate the unit vector of this gradient vector, then it will result in same as xi plus yj divided by square root of a square x square plus y square. Same as what we calculated the gradient vector of a circle, that is x square plus y square equal to a square. So I was actually trying to say what is behind the scene. Now let's move on and get ready to calculate the gradient vector on the fly itself. But understand that what is behind the scene. So let's consider the paraboloid. As we have stated that there are two conditions of gradient vector. One is through algebraic equation. One gradient vector comes through algebraic equation. What is algebraic equation for this paraboloid? So algebraic equation for this paraboloid is x. Algebraic equation for this paraboloid is z equal to x square plus y square. X square plus y square minus z equal to 0. So let's not go if it is 3D, let's not go into 4D and calculate the density, partial derivative. Let's on the fly, let's calculate the kind of gradient vector. So if equation is x square plus y square minus z, then what is gradient vector? 2xi plus 2yj minus 1. If that is the case, then if this is the if that is the case, then if it xy plane, if that is the case, then if this is xy plane and blue line, what we see at the center is center and it is kept like this at the center, then at the origin, when x is 0, y is 0, then what is the gradient vector? Okay, gradient vector we calculated at 2xi plus 2yj minus k. X0, Y0, then gradient vector is minus k. Means if this is kept at origin, then the gradient vector is like this, minus k. But as x and y is increasing, the z component of gradient vector is always minus 1. I mean k component of gradient vector is always minus 1. But as x and y is increasing, let's consider x-axis. This is x-axis, this is y-axis, this is xy plane. Let's move on x-axis where y is 0. So if x is keep on growing, so gradient vector start moving like this and slowly it becomes horizontal because the minus k is little bit tilted where x is very strong. So gradient vector, if I calculate the surface of a paraboloid, then it is always perpendicular to the surface. Can you see this everywhere? What about if I take this algebraic equation as position vector, then what is the gradient vector? Let's consider the case of a sphere. Okay, then you can calculate this in kind of in I believe in cylindrical coordinate system. Anyway, let's take a case of a sphere. This is my sphere. Okay, oops. So this is really a kind of okay, this is very nice sphere. Okay, if this is a sphere, if this is a sphere, then what is the equation, algebraic equation of the sphere? X square plus y square plus z square equal to a square. What is gradient vector? 2xi plus 2yj plus zk. If that is the case, 2xi plus 2yj plus 2zk, x square plus y square plus z square. If that is the case, then every moment consider the case where x, y, z are equal. If this is centered at origin, then this is x-axis, this is y-axis, and this is z-axis. Somewhere here, x, y, z are equal from x, from y, and from z. Then it is 2i plus 2j plus 2k, considering x, y, z some equal point, I plus j plus k. So from origin, if I draw a line to 1, 1, 1, then it points like everywhere it is perpendicular to the surface. That is 2xi plus 2yj plus 2zk. Okay, if that is the case, then let's go ahead and calculate what is the gradient vector where I represent this sphere. If I represent this sphere as position vector, if I represent this sphere as position vector, let this is centered at origin. If this is centered at origin, then if this is centered at origin and this surface is like this, then from origin, this is the position vector of the surface. The end point is touching the surface. Oops. Okay, small one is vanishing. Anyway, so if this is centered at the origin and this is the radius, consider big ball, then if I move like this anywhere, so this is the position vector. If this is the position vector, this is point P touching the sphere surface. So this is inside the origin. If this point is is at the origin. If this point is at the origin, if I move this like this, then it is touching the surface. So any point P, if this is centered, if this is centered at origin, if this is centered at origin, then any point P is x comma y comma z, x comma y comma z. Then position vector is xi plus yz plus zk. Then xi plus yj plus z. Z is the square root of a square minus x square minus y square. So xi plus yj plus square root of a square minus x square minus y square k. Okay. Now someone has to calculate the gradient vector for this. Gradient vector is nothing but whatever we gradient vector is, if this is vector f, consider this vector is f. I'm talking about capital F. Consider this vector as f. Then we are trying to calculate the gradient of f. Gradient of f is nothing but df by dx I plus df by dy j plus df by dz k. Okay. So I'm sorry. Consider to get the gradient of this vector, not the gradient vector. If I have a small f as algebraic function, then gradient vector capital F is df by dxi plus df by dyj plus df by dyz df by df by dxi plus df by dyj plus df by dzk, where f is small f, that is algebraic function, and we are trying to get the vector field or gradient vector capital F. If I have a position vector that is xi plus yz plus square root of a square minus x square minus y square k, for this position vector, what is its gradient? Each component I have to derive, and I have to do the differentiation along x-axis, along y-axis, along z-axis, or along any particular axis if it is a kind of a parametric vector. Parametric vector where we have only one independent component. To have parameterization for the vector xi plus yj plus zk, or square root of a square minus x square minus y square k, xi plus yj plus square root of a square minus x square minus y square k. If that is the case, then this is not a parametric vector. Parametric vector should have only one independent variable. Here we have two independent variables as x and y. I can consider this as parametric vector only when if I have considered xy plane as independent variable, not x-axis and y-axis as two independent variables. If that is the case, then I have to club x and y together. Please concentrate here. So now I have a vector, position vector as xi plus yj plus zk, or square root of a square minus x square minus y square k. I have to get the gradient of this vector. Gradient, to calculate the gradient, we can calculate based upon one independent variable. But here x and y are two independent variables. I can consider x and y plane as one independent variable. If that is the case, xy plane as one independent variable, xy plane as one independent variable, then how I can proceed and calculate the gradient of this vector? Someone has to do research on it. This is what I would say. If I have a position vector of a sphere at xi plus yj plus square root of a square minus x square minus y square k, and if I try to calculate the gradient of this vector, then independent component should be only one. But there are two independent components x and y, and we cannot do anything about it because they are really two independent components. What we can do is we can consider x and y two independent components as single independent plane, that is xy plane. If that is the case, then we have to derive this f vector df by dxy plane, df by dxy plane. Okay, d by dxy plane. If that is the case, then someone has to think that how I can define xy plane, and then I can do the get the gradient vector. Let's see gradient of this vector. Let's transform into spherical coordinate system. Now the fifth one came into the picture. We have numerical science, then we have algebraic science, then we have vector science, we have calculus science, and then we have multiple coordinate systems, and we have tutorial from everything. Now in multiple coordinate system, we can convert into a spherical coordinate system. In a spherical coordinate system, there are three variables. One is radius, that is varying from 0 and it is growing till it is touching a surface of a sphere, radius. One is that if there is a perpendicular z-axis, from there it makes phi angle, and from there it grows till the 2 to pi, from 0 to pi, 180 degree, 0 to pi. this forms a kind of a arc. In vertical scenario, it forms an arc. Okay, so if I combine varying radius which is varying from 0 to full radius, one angle that is varying from vertical axis, it takes angle from vertical axis, and from there it is going to 180 degree, and then in xy plane, if I take a theta angle, and theta is varying in 2 pi 360 degree, if I take these three things, then all three are orthogonal to each other. If theta is angle, then arc what it is making, the arc what it is making, this arc, and perpendicular this arc, high angle arc, high angle arc, theta arc, they are perpendicular to each other. And then this radius r radius, again it is this r is perpendicular to the phi arc, and on xy plane this radius is again perpendicular to the theta arc. So all three are perpendicular to each other. So if I take any point P on the sphere, then anyway, for the algebraic equation we have calculated the gradient vector, that is x square plus y square plus z square equal to a square. Then gradient vector is 2xi plus 2yj plus 2zk, that we have already calculated. If I have any point P on the sphere, then a spherical coordinate system, what is its coordinate? Then it is a. A is radius of the sphere. If this is angle phi, if this is angle phi, and this is a sine phi would land into xy plane. A sine phi and then cos theta is x-axis. A sine phi sine theta is y-axis. A sine phi cos theta, a sine phi sine theta. Okay, these two falls in xy plane. Okay, and then a cos phi is z-axis. So can we say that I have three components as a sine phi I plus a sine phi cos theta I plus a sine phi sine theta j plus a cos phi k. So this is the position vector of any point P. This is phi angle, a sine phi cos theta I, a sine phi sine theta j, and a cos phi k. Now can I club together I and j? Now it is a sine phi and in braces cos theta I plus sine theta j, bracket close, and a cos phi k. Now we have more or less x and y component together, that is xy plane and k. Now let's differentiate it with phi. Okay, we will move on. We are not saying this is the end. Let's differentiate with the phi. If we differentiate with the phi, then it becomes a cos phi, and in braces cos theta I plus sine theta j plus minus a sine phi k. When phi is equal to 90 degree, means when we are in xy plane, phi is 90 degree. What is value? D position vector dp by d phi, that is a cos phi, a sin phi, a cos phi in braces cos theta I plus sin theta j minus a sin phi k. If that is the case, when phi equal to 90 degree, then a cos phi is 1. So a cos theta I plus a sin theta j, that is the gradient of this vector, minus a sin phi. So a minus Okay, pi by 2. I'm sorry, means we made a mistake. Okay, let's see again. The equation, actual equation is a sine phi, a sine phi in braces cos theta I plus sine theta j plus a cos phi k. This is the position vector. dp, this is p, dp by dp by d phi. Then it becomes a cos phi. A sine phi becomes a cos phi. A cos phi cos theta I plus sine theta j minus a sine phi k. If that is the case, then cos phi, when pi, this is the phi is 90 degree means xy plane. When phi is 90 degree, cos 90 degree is 0. So this term I component and j component gone. Now we have minus a sine phi k. Sine 90 degree is 1. So minus ak. So when it is at equatorial of earth, then it is like this. Can you see this? Minus k. This is the gradient of the position vector. When phi is 0, then a cos phi, that factor is 1. Then it is a cos theta I plus a sin theta j. Sin phi factor is gone. Means at the polar side, then it has only I component and j component. So based upon the theta, it will keep rotating like this, parallel to the xy plane. So when it is in xy plane here at equatorial, then it is perpendicular, like it is in z axis. Here it is like this. This proves that it is tangent to the surface. So if I take position vector, if I take the equation of a sphere, this proof is not available anywhere else. This is our proof. So if I have a sphere and if I have any point P and I have a position vector at P, if I have a position vector at P, I have a position vector at P, then for that position vector, the gradient is a cos phi in braces cos theta I plus sin theta j minus a sin phi k, and this gradient vector is nothing but tangential to the surface. Okay, but anyone would ask, if it is tangential to surface, then at this point tangent can be like this also, but no, it is strictly minus k. So this proves that this tangent is going towards maximum slope. So this tangent, if it is tangent, it is 3D, right? At the end it is 3D. If it is 3D, then this tangent can go anywhere, but it will move only in direction of maximum slope. What I am trying to say, that equatorial, if it is centered at origin, then xy plane would cut it at the center. If that is the case, then at that moment, if this is the tangent, if at some z value, if there is some z value, if I cut it again, cut at the xy plane, then cut there again, okay, and at that moment and this moment, this is the point at xy plane equatorial, and there is one more point on the top, there I have made a cut. This would go in a direction to the next. So this is one contour, that is z equal to 0. There is another contour where z equal to 1, 2, 3, 4, whatever the value is. From z equal to 0 to z equal to 2, this gradient vector would proceed in a direction where it is of minimum distance. Sharpest slope it will write. This explanation you will see in the book, that it goes through the sharpest slope, but no one talks about how. Everyone will draw gradient contour diagram, and then it will show tangent to the contour, and then nonsense. So there are two gradient things that we see what we are saying. One gradient is perpendicular to the surface. That if I take algebraic equation as x square plus y square plus z square equal to a square, and that we calculate the gradient vector in form of 2xi plus 2yj plus 2zk, then gradient vector is perpendicular to the surface. Okay, everywhere it is perpendicular to the surface. But if I take it as a position vector, then gradient vector is actually tangential to the surface. Whatever it is, either it is perpendicular to tangential, but it will move point to point in a direction where it will reach the peak from equatorial in minimum distance. That will be the direction, not anywhere it is rotating like this. Okay, that is the same, because the gradient vector is a cos phi in braces cos theta I plus sin theta j minus a sin phi k. Please take it as homework and then see that it is really going in a sharpest slope. Okay, the quickest from the equatorial to the top, from the quickest slope it is going. No, it is not meandering here and there. Someone has to prove it. Okay, so more or less gradient vector in 3D we have calculated. Someone has to calculate. If I take position vector in paraboloid, that is xi plus yj plus x square plus y square k, then what would be the its gradient? Someone has to calculate in polar Cartesian or cylindrical or spherical, whatever it comes to his mind. So anyway, so later in the session we will see the importance of gradient vector, and then we'll move to curl and flux. So these are extension of gradient vector only. They are called velocity vector, vector field, whatever. So that we will see.